Welcome. So I'm Christian Stenner, and I'll be talking about glaciovolcanic cave research in the USA and Canada. So through this presentation, we'll be talking about some of the glaciovolcanic cave systems that exist in the Pacific Northwest and as well in Canada. We'll be discussing some of the cave systems, their similarities, their dynamic nature, their morphologies, but we'll also be talking about some of the interdisciplinary research that has happened within them. So that includes some microbiology studies and studies of the microbiological communities that have been found within the cave systems. We'll be talking as well about some of the climatology work that has happened to describe the hazardous atmospheres that may be present and some of the microclimates within the caves. Lastly, we'll talk a little bit about some of the robotic testing that has happened in these subglacial environments, recognizing that these caves can be good analogs for other icy bodies in the solar system. So with that, let's get into the interdisciplinary glacial volcanic cave research in the USA and Canada. First off, we should talk a little bit about what are glaciovolcanic caves. So this is a new term, and it relates and derives from the term glaciovolcanism. So glaciovolcanism could be described as the interaction of heat from the Earth's interior with various types of ice masses. So any of those interactions that are derived from volcanic environments can be considered glaciovolcanism, and the void spaces that can occur from those interactions, void spaces being caves, could be considered glaciovolcanic caves. So here's an example of what we're talking about. So here we can actually see the steam coming out from the crater of Mount St. Helens, and that's interacting with the crater glacier. So within the crater glacier, that's one of the environments we'll be talking about, and a system of glaciovolcanic caves is formed in the glacier, primarily formed by fumarolic emissions, so steam and gas emitted subglacially and causing the melting of glacier to form void spaces. So we can see that there have been many ways that these sort of systems have been classified in the past. Halliday identified glacier pseudokarst as one of 8 pseudokarst typologies. So that included endglacial conduits and included glacier caves formed by meltwater, but it was also a part of that paper that identified the geothermal examples of the glacier cave typology. So that included the examples which are well known at Mount Rainier and also some other ones at Mount Hood and Mount Baker, which had been studied earlier. So if we further categorize them as glaciovolcanic caves, it helps to recognize that they have a volcanic origin. And so the caves that are formed in ice masses and glaciers, could owe their origin to the advection of recharging melt from above, but also from the thermal flux from below, or the combination of those two. So the ones that we're talking about primarily owe their genesis to the thermal flux. And so from that, I think it makes sense to differentiate them from glacier caves, where the primary mechanism of formation is by meltwater. So another way to classify them could be as phase change caves. So we see other volcanic caves that are a result in phase change. So I think that makes sense as well as a way to differentiate them. Other ways that they've been differentiated are via the medium, the cryospheric medium that they've formed in. So a lot of them have been called fern caves. So in Mount St. Helens, the cave system that was identified by Anderson and others around the 1980s lava dome was called a fern cave system, and that owes to it being developed in the fern zone, where the density was between 400 to 830 kilograms per cubic meter. So that's certainly a very applicable designation. But we've also seen some of the caves can go very deep within these glacial areas and can transmit through the firn zone and into glacier ice. So where we see the glacier density, we can actually see the fern glacier transition from viewing the ice. Sometimes we can see that, or by taking samples for testing the density of the ice. So we can see a hybrid in that some of them aren't just fern cave systems, they aren't just glacier cave systems. They actually will exist in both zones. So one other way then to describe them is in relation to their genesis. So rather than just relying on fern cave or glacier cave and then causing perhaps some confusion with those formed by meltwater, we could describe them in relation to their genesis from the volcanic system. So nearly all of the caves that we'll describe in this presentation are owing to the hydrothermal system. So many of those from fumarolic emissions. I would say, 95, 99% of them appear to be fumarolic in origin. But there is one example that we'll talk about, which is owing to warm springs that emerge subglacially and in combination with the airflow have formed a cave system as well. So they're not just a fumarolic emission of heat or steam or gas, but also from heated water coming up subglacially. Now, there's also a lot of evidence in areas around the world, such as places like Iceland and British Columbia, and certainly where glaciovolcanism has a lot of research is in subglacial eruptions that have happened in the past or could happen in the future. And so we see evidence of those where an effusive eruption has perhaps been occurring subglacially, and that could form a void space as well. So we don't have that example in the Pacific Northwest, but perhaps there are places in volcanic areas where it's happened, namely in Iceland especially, that could be occurring right now. So if anyone goes into one of those caves while it is in eruption and could take some photos, we'd certainly appreciate that, but that would be something I think would have to be very carefully considered from a safety perspective. Okay, so glaciovolcanic caves can exist in a lot of different areas because we know that Edwards and others had identified 245 Holocene volcanoes as impacted or having potential impacts due to surrounding ice. So despite this, we only see a few places where that interaction has caused void spaces to form that have persisted, so are still in existence right now, and have had research published that we can refer to. So those are the ones in red. So we see them in the Pacific Northwest, in Canada, and in Antarctica. There are a number of other places, and those are the ones identified on the map in yellow, where we have either anecdotal evidence, so things have been reported on the internet, or there's been some photos or other references made to void spaces in combination with volcanic activity. Or these are the ones which have been reported in literature previously but have since disappeared, or they have collapsed, or the volcanic activity ceased and the void space isn't in existence anymore, or they're unconfirmed. So it could be that the research was done in the past, but in the 30 years since, nobody has been back to confirm whether it's still in existence or not. So even with those added to the total, you can see that there are not many places around the world where there are glaciovolcanic caves. So the investigations of glaciovolcanic caves that our team has conducted and other teams have had many different aspects. We're looking not only at the geochemistry underground, we are looking at the microclimates and the climatology that can happen in relation to the caves, whether it's the internal climate or influences of external climate, and the morphologies themselves. We're looking at comparative morphologies over time. How are the caves expanding or contracting? So those interdisciplinary studies have had a number of forms, and some of that relates to seeing if caves can be a barometer for volcanic activity. Is the expansion or contraction of the caves, is the measurement of subglacial fumarolic activity indicative of anything in relation to the hydrothermal systems? So are there changes in cave volume that can be related to other parameters that can help us to understand these volcanoes a little bit better? And these are good analog environments for icy bodies of the solar system or places which have lava tubes and cave entrances such as the moon or Mars. So there's definitely some good evidence for these being analogs, and we've used them as such for the robotic testing, but as well for studying the microbiological communities that can exist in these extreme environments. And then in places like Mount Rainier, where many mountaineers will traverse over the cave system in their quest to reach the summit, there are in-cave hazards. So not just unstable slopes underground, but also volcanic gas emissions can cause things like lakes of carbon dioxide underground, buildups of volcanic gas. And for search and rescue operations, it's important to map the cave systems and know what is there. And those maps can also be used for education and for modeling and making great figures in your paper. So the other part is for wilderness stewardship and conservation education. And one particular example is, again, the summit of Mount Rainier, where this is a national park environment, and there are a lot of people potentially, at least visiting perhaps a cave entrance in their quest for the summit. Well, these are very important and delicate environments, and as such, some conservation education could be important for preserving those for future research. So this diagram shows a little bit of some of the interdisciplinary studies that are happening. So the hydrothermal system in the center, we have geochemistry, cave climate, the internal and external influences there. All those things influencing the environment for what can grow and what can live there, the geomicrobiology at the top. And then the cave morphology is at the bottom, so we can have a look at what sort of changes are happening in the morphology, and is that related to changes in the hydrothermal system. All right, so now with some of that background out of the way, let's take a tour of some of the Pacific Northwest glaciovolcanic cave systems. So at the summit of Mount Rainier, there's an overlapping east and west crater, and these host the world's largest glaciovolcanic cave system. So the caves have been known about since the first authenticated summit climb in 1870. However, studies had not been done until much later in time. So here in the image, you can see the east and west crater. And as a bonus, you can see the crater of Mount St. Helens in the background, which makes it, I think, a really amazing image. So yeah, we have the east crater, which is much more defined on the left-hand side of the image, and then the west crater on the right-hand side. So the first sketch map done by Nelson and Whitaker was in 1970. And it was shortly thereafter that Project Crater was a very large study that happened for the Mount Rainier cave system. And Kiver and Steele's paper in the NSS Bulletin published a map of the east and west crater cave system. So at the time, they had mapped out 1,700 meters of cave passages in the east crater system and over 300 meters in the west crater cave system. Within West Crater Cave, a subglacial lake called Lake Muriel was identified as the highest elevation lake in North America. So a lot of work was done to describe the cave morphologies at the time, and definitely we owe a lot to these previous studies that had happened in the 1970s. So the most recent studies were done between 2015 and 2017 by Glacier Cave Explorers, which is a group of the Oregon High Desert Grotto of the National Speleological Society. So the most recent map plotted on Google Earth imagery would show you this. So at first glance, we don't see much of a change from the previous 1970s mapping efforts, but there are some distinct differences, which we'll go into. All right, first off, one of the similarities is the master passage, which is a curvilinear around the East Crater Cave. It exists as a master conduit linking a number of dendritic passages which follow the rock ice margin towards the crater rim. This is an example of the largest room in the East Crater Cave system. It was named the Colosseum by Bill Loki in the 1970s, and it's still there. So we see large portions of the cave system which have showed a static morphology even after 50 years. So this is an example of that master conduit which exists. A new feature which was found in 2014 is this lake. So Lake Muriel previously was the highest elevation lake in North America. Well, as of 2014, Lake Muriel didn't appear to exist anymore. However, this lake in the East Crater Cave system was discovered and named Lake Adelai. So this one, if we were to continue that designation, would be the highest elevation lake, the new highest elevation lake in North America. It's just that it's in the East Crater and not the West Crater now. So if we have a look at the most current mapping efforts, we actually see that the East Crater Cave has doubled in length, in surveyed length to over 3,500 meters and a depth of 144 meters. Now, that's not necessarily indicative of changes in the hydrothermal system of the volcano. What we actually see is that there is an extension in passages. So on the west side of the crater, this extension of passages of almost 600 meters of passage is new. That is new. And a lot of the passages, the dendritic passages which go along the crater rim are constantly changing. So in all of the different surveys that have done all the way back to the 1970s, we see that is a very dynamic area. But the master passage, which is a curvilinear around the crater, is for the most part has been static over 50 years. So that's pretty interesting to see. So one of the ways that we could describe potentially why that is happening is a paper done by Floria and others, which showed some complex associations between the external weather and the internal measurements in the cave. So we see actually an increase in cave temperature and air pressure over winter, which we believe is related to in winter the entrances, many of the entrances likely are covered in snow. So we actually see an increase in heat underground with a buildup of heat and air pressure there. So here's an example of one of those entrance areas that we believe is very dynamic. So these are changing constantly. They may change with a seasonality every winter, but the heat flux seems to find new ways to get to the crater rim. So if we envision that in the 3D model, we can see the curvilinear passage, but all of those entrance passages which rise up to the crater rim showing a very consistent morphology all along this 35-degree angle slope that rises upwards, whereas the laterally oriented master passage, which is more static, has very little slope, and it tends to be more laterally oriented, again in this sort of circumcrater curvilinear shape. All right, so moving on to Mount St. Helens. So in this image, we can see the crater of Mount St. Helens, over 1 mile wide, and the lava domes. There's 2 separate lava domes that have built up in the center. The first one up into the mid-1980s, and then the second larger one, which built up between 2004 and 2008. So Anderson and others had mapped a system of fern caves around the old 1980s lava dome, but the buildup of the 2004 to 2008 lava dome would have obliterated all of those caves. And it's since 2012 that a new system of caves has started to be seen and explored around the 2008 lava dome. So that's a new system which is in continual expansion. Whereas we see the Mount Rainier system has been largely static with segments of dynamic morphology. There's a lot of dynamic morphology in the Mount St. Helens system. So here's an example of what's happening. We see the crater Glacier as it has been expanding and actually building up. So this is a glacier that is expanding, not retreating. That is encroaching now on fumarolic areas around the lava dome. And so we see as it encroaches on those areas, we see areas where there are cave passages now developing in the glacier which did not exist before. And when we map out those caves over the last few years of exploration, we've now found over 13 distinct glaciovolcanic caves within the Mount St. Helens crater. So this is the latest as of June of 2021. So this is brand new information. Over 3,000 meters of total length of all of the caves combined. And the majority of these are around the 2004 to 2008 lava dome. And that's the south end of the map, which is at the top of the image. And on the northern side, we have 3 caves on the bottom left, which are in the fern area. And they are just on the side of the 1980s lava dome. So here's an example of what we're seeing from the studies of the cave morphology. Crevasse Cave is one of the caves that was first discovered and mapped in 2014. And over a 4-year period, we've seen this extension northward. So the entrance, the northernmost entrance, was actually the rock-ice interface as it previously existed. But as the glacier has advanced around the lava dome and built up in elevation around the dome, we actually see that the cave has expanded along with that. And so we see over 100 meters in further extension to the north in a 4-year time frame. So many of the caves you could believe should be forming in its perhaps as a chimney type formation. And here's the first one that was found in the Mount St. Helens crater of the new system of caves, I should say, called the Godzilla Hole, and descended in 2014. So you would assume perhaps that heat from a subglacial source would rise and cause these holes to breach in the surface of the glacier. But even in descending this, the Godzilla Hole, another entrance was found which followed the rock ice margin up to where the rock ice interface was against the lava dome. And so we're actually seeing in this example here of a diagram showing a glaciovolcanic void, so a cave on the left and a chimney on the right, that we're seeing that there is almost always a lateral expansion of the cave as well. So the heat is rising upward, yes, but also laterally in almost all of these cases. So we see a few examples of chimneys. Here's one from Mount St. Helens in September of 2020. Where an existing cave, which had a very high ceiling chamber, very high such that it was close to the surface, eventually actually the snow had either collapsed or there had been some ablation that we believe had caused the chimney to open to the surface where there hadn't been one before. So we do have a few examples of that. One where we believe that the primary mechanism of cave formation was glaciovolcanic, but then it exploited a very large crevasse, and so it has formed a persistent chimney-like opening. So the majority of these caves, however, do not breach the surface directly over the areas of fumarolic heat. Instead, they appear to have this mechanism where they are cave passages follow the rock ice margin, and there will be a passage sort of, in this case in Mount St. Helens, we see it sloping towards the lava dome. But in other examples, such as at Mount Rainier, we see it sloping towards the crater rim. So even where the cave enlarges, because in Mount St. Helens, the glacier is still accumulating snow and rock debris every season, the entrance passages move further up the lava dome, and even if the cave, the master lateral passage enlarges, we actually don't see it necessarily breaching the surface. So here's an example of those entrances that we can see. This is one area where there's a concentration of numerous entrances in a fumarolic area against the 2008 lava dome. So if we look at all those in a profile view, we can see that there is, yes, a lateral expansion along the dome, but again, those entrance passages typically rise along the slope of the lava dome towards the rock ice margin, rock ice interface. So as long as the glacier continues to build, then I think we'll see expansion of the cave systems to continue. So this example showing, again, we're actually looking down one of the lateral passages towards the figure in the distance. But you can see the slope of the majority of the cave morphology follows the slope of the lava dome. So the entrance is being towards the top right of the image, following that. That's a good example showing the slope of the rock of, perhaps 45 degrees in this example. So we can also see lateral passage development as well. So on the right-hand image, the 2018 survey of the cave superimposed on past satellite imagery, we can see the portions of the cave which couldn't exist because there just wasn't ice there at the time. And then another visualization is on the left-hand side, where we can see the 2018 satellite imagery and the 2018 cave survey, but in blue dotted line, we see the past rock ice interface and how the caves will expand laterally as well, as long as the fumarolic output were to remain the same and the rock and the ice were to continue to build. We expect that the caves there will continue to expand until they reach a point of dynamic equilibrium, similar to what we have seen at Mount Rainier. So we have two examples there. We have one that's just largely static at Mount Rainier and one which is very dynamic at Mount St. Helens. Interesting to note is that almost all of the cave morphologies have a floor which is composed of the volcanic rock, the breakdown or the sediment in Mount Rainier and Mount St. Helens. However, there's a couple places where we've seen this type of morphology where a raised tube, which is completely formed in ice, has formed. So additional study is necessary to determine why is it formed above the regular sort of bedrock passages. Why is a raised passage formed completely in ice? So that's an interesting thing that we've seen on a couple of occasions. So this rotation shows all of the different Mount St. Helens caves around the lava dome. Just in the foreground there, the longest one is named Rodan Cave, just most recently mapped in June 2021 to about 780 meters in length, which would put it as second longest in the world, up against the 3,500 meters of the East Crater Cave of Mount Rainier. So in Canada, we have one known example of a glaciovolcanic cave system, and it's in the one known example of an active volcano in Canada at the Mount Meager volcanic complex. So here we see an image of that, and you see the people there for scale of a cave entrance in the Mount Meager volcanic complex. So similar to the Cascade volcanic arc, the Garibaldi volcanic belt is the Canadian equivalent. The Juan de Fuca plate and the subduction of that under the North American plate is the cause of a lot of the volcanism in this area. And so in red, we see the location of Mount Meager circled there. So Mount Meager is interesting for a lot of reasons. It consists of a lot of hydrothermally altered rock. And in 2010, the largest recorded landslide in Canadian history occurred at Mount Meager. So it was 53 million cubic meters of rock came off of the side of Mount Meager. This image shows a number of the other still unstable slopes in existence. So there's 27 identified unstable slopes on Mount Meager, which far surpass the 53 million cubic meters of rock from the 2010 landslide. So in addition, on the image here, we can see two green triangles in Job Glacier, which were the fumaroles identified first in 2016. So those are the ones which we are considering to be glaciovolcanic caves. So in this image circled, we can see in the distance one of the entrances there in the glacier at the Mount Meager volcanic complex. So in the large image I showed you at the first introduction to the Mount Meager system, that is the one identified as 1A in this diagram. And so we've seen changes over the past 4 years. This image from about August of 2020, we actually see 1B, which is a very large chimney which has formed perhaps 100 meters distance from the initial very large entrance. And so you can see the size of what that chimney must be, given what you saw of the size of what 1A was in the initial image. We also see number 2, which is a very large area, fumarola heat, which has caused a breach of the ice, and then another skylight, number 3. So this is constantly changing and evolving as well. So we have a very dynamic system, but very limited on-ground observation. So there's no surveys done of the cave as of yet. And the reason being that this cave is complicated by large amounts of hydrogen sulfide, which are being emitted from the subglacial fumarole. So this image shows you another example of the scale of that large entrance, again, number 1A in this image. And the steam, the amount of steam that is coming out of the cave system, which is also mixed with hydrogen sulfide. So around the area, we would need air purifying respirator masks. And the initial entry into the cave was done with a self-contained breathing apparatus. So one thing to note is that the majority of these caves, along with others found on Mount Erebus in Antarctica, have not shown large accumulations of volcanic gases. However, the Mount Meager system has shown at the entrance up to 200 parts per million of hydrogen sulfide. And the Mount Rainier system, in particular, the West Crater Cave, has shown large accumulations of carbon dioxide. And I'll get into that in a little bit there. But both East Crater Cave and West Crater Cave in Mount Rainier both have large accumulations, areas which have accumulations of carbon dioxide, which would be of immediate danger to life and health. All right, moving on to Mount Hood. Now, this is a very special example, which I really wanted to get into because it's different from the fumarolic examples. So this is the one, what I mentioned is we have warm springs actually being discharged subglacially. The circle there is just to highlight one of the dangers. At Mount Hood, and in particular at Mount St. Helens, the amount of rock that's in the glacier ice shows its face in the walls and the ceiling of the caves. So this is very much a hazard because they will melt out as you are standing there, and certainly something to be aware of. But this image is more so to show the stream that's actually flowing through the cave system here, which is the focus of our points that we'll make. So the snow dragging glacier cave system is in the Sandy Glacier at Mount Hood. And you can see 3 branches there to the cave as it was mapped as of 2012. So at that time, 2,185 meters long and 292 meters in depth was a very significant glaciovolcanic cave system. So if we look a little bit closer, we can actually see some of the changes that have happened. So the red lines on this segment of that cave system, called Pure Imagination, separately named, is in 2012, we see a red line where the entrance to the cave existed in late 2012. Then it moved in June of 2015, and then it moved again in October of 2015, and it has moved significantly since then. So here is a cave which is in retreat, along with the glacier that's in retreat. So we have an example here of a cave that's very dynamic, but is shrinking. In comparison to Mount St. Helens, which is growing. So here we see the reason for, partially the reason for the existence of the cave is over 48 warm springs found in the cave system, and one part in particular which was separately named Hot Imagination Cave, where there's quite a concentration of warm springs. Now, these were discovered using thermal imaging. So we use thermal imaging as part of the climatology studies throughout the cave systems to map the locations of the subglacial fumaroles or areas of heated bedrock or sediment which can exist underground. So this example here showing one of the fumarole vents where you can see the sort of vent entrance in white. But in Hot Imagination Cave, so this is a remnant of that snow dragon cave system. Hot Imagination itself, when last surveyed, 2017, was about 200 meters in length. So we're talking a cave system which went from 2,100 meters now to one remnant of it, in particular 200 meters, showing the amount of ablation which has happened and the reduction in length of the system. However, here, the image, what we're demonstrating is this is a stream of the warm spring water of over 20 degrees on the right-hand side, which is mixing with a cooler spring water. Now, cooler being, we're looking at 16 degrees here, and it's all mixing around a large rock, which is in the middle in black. So we can see that at least part of the Snow Dragon cave system owed its existence to heat of subglacial springs. There are no fumaroles that had been located in this cave, so that's maybe one example of a glaciovolcanic cave typology that exists that is not fumarolic in origin. So along with the climatology studies, many of our studies have involved anemometry. So a series of anemometers placed throughout the cave system, which can measure the temperature, the humidity, and minute changes in the airflow. And what we're seeing is definitely some complex associations between the thermal output and then the wind that may come from top entrances and lower entrances, chimney effects, and so forth that have caused these cave systems to form. So, it's a matter of both the fumarolic heat and a combination of the airflow, which is causing these. That's my very scientific explanation of the climatology. Okay, moving on. I'm not a climatologist. When we looked to some of the hazardous atmospheres, so again, very few places have had hazardous atmospheres. However, in the west crater of Mount Rainier in particular, some of what we found was pretty interesting in that there are a few places that even though there are air circulation effects, there can still be accumulations of carbon dioxide that are above levels which are of immediate danger to life and health. And that these lakes, so-called lakes of carbon dioxide, the boundary level of where they were of dangerous atmosphere to breathable atmosphere would vary. It would vary on occasion. So you could literally be standing in a lake of unbreathable carbon dioxide and breathing perfectly breathable air and not know where that boundary was. So there are a few places there where carbon dioxide accumulations calculated from measurements of oxygen depletion were found to be above 24% carbon dioxide. And then in the East Crater Cave, over 10% of carbon dioxide. So these are certainly well above levels that are immediate danger to life and health. And they required self-contained breathing apparatus to fully explore. So these diagrams showed a couple examples of influences on the carbon dioxide levels in relation to different other atmospheric conditions, such as a warm air outflow and a cold air inflow in the West Crater Cave. Now, one of the things that we found is that there was definitely a change in the carbon dioxide concentration levels, which correlated to atmospheric pressure. So we could see the level or that boundary change with differences in atmospheric air pressure. All right, onward to some of the microbiology studies. So this is definitely very interesting. As mentioned, these caves are extreme environments. They're oligotrophic environments that harbor microbial communities, which are very unique. So they're analogs for subsurface marine environments, but also for Martian and lunar caves. So first off, we want to discover, well, what's even living there, if anything at all. And so a number of studies have been done, which are still ongoing, specifically in the Mount St. Helens caves, from which this diagram is derived to support those. So we're looking at some of these extremophile microorganisms that are living at the edge of existence. So for example, using chemoautotrophy for survival. And as well, a lot of the sample collections for these studies are happening during the initial exploration of these caves. So there's little to no human contamination. They are pristine environments which had not seen human visitation, and perhaps on their first ever visit are the sediments around fumaroles in particular are collected as part of the microbiology work. So a diagram showing the different types of studies that are happening from the sediment samples that are analyzed. Certainly we're finding out about the geochemistry, but then further about what is actually living there. And so from doing microbial culturing and a metagenomic sequencing of the microbial communities, we can infer their metabolic lifestyle, but also to potentially to mine them for antibiotic genes. So there's definitely a number of the microbes which have found to have antimicrobial properties in the Mount St. Helens cave system. So those studies have been headed by Roberto Anatori and Rick Davis, pictured here. And so we see some of the sample tubes from the one of the Mount St. Helens crater caves from sediments within the caves. So those sediments, we have done further metagenomic sequencing. This phylogenetic tree is showing some of the metagenome assembled genomes. And so from that, we see predominantly aerobic, mostly bacterial communities in the cave sediment samples from Mount St. Helens. So the fumarole temperatures ranging from 7 to 40 degrees Celsius. So not necessarily very super hot fumaroles, perhaps just warm sediments that were where these bacteria were living. And so far analysis of the metagenome assembled genomes showed communities are dominated by bacteria, and some of them are capable of fixing inorganic carbon using the Calvin cycle while oxidizing carbon monoxide and or hydrogen to produce energy. And as well, the additional studies have shown, as I said, that some of the cave bacteria are producing antimicrobial compounds, which is really interesting. So they're definitely, the environments are harboring undescribed diverse microbial communities, which are using trace volcanic gases for growth. All right, and lastly, as I mentioned, these have been used as testing environments for robotic technologies meant for exploring icy bodies of the solar system. So in particular, Jet Propulsion Lab has produced this concept prototype called Iceworm. And so in the crater of Mount Rainier, they tested the end effectors, so the ice screw components, which are built around a commercially manufactured ice screw. And then in Mount St. Helens, they tested the prototype of the entire robot called Iceworm. And so it made its first steps up one of the ice walls in Mothra Cave in Mount St. Helens, and that's the photo of that test. So other examples are being developed, and there's many examples being developed for exploration of extreme environments, and caves being one of them. So lunar lava tubes are one example, and JPL has as well another concept called the Axel Rover, which as part of the moon diver concept would be something that could explore lava tubes on the move. So this is sort of like a rappelling rover, which would rappel down into a lava tube to do exploration. And the ESA has gotten into this as well. So there's a lot of recognition of these environments as being worthy of study, being sheltered from solar radiation, and perhaps being a good prospect to find microbial communities or evidence of past life. So the ESA has Daedelus as one of their concepts for exploration of cave environments on other worlds. So hopefully we see one of these sort of missions get the green light to go forward and do some exploration. But until then, glaciovolcanic cave environments have a lot of characteristics which have proven themselves to be beneficial. So we have perhaps similar microbial communities as to what might exist on other planets. We have cold, dark environments, and we also have sources of geothermal energy. So these can be good analogs for other places which have similar characteristics. All right, and that brings me to the end of the presentation. So I am the presenter, but there are many people who contributed directly to the research, many of which are listed here and some of which I've probably forgotten. Unfortunately, there's been a lot of people who have contributed to these studies, both as part of the Glacier Cave Explorers group and as part of other research teams. And as well, all of the support people who happen to make these studies happen. In particular, at Mount Rainier, over 100 people were required in and amongst the different expeditions to porter the scientific equipment up to the crater and back down again because a lot of equipment was necessary to complete some of the work. And so there was a lot of logistical support, medical support, safety personnel, and so forth, along with all those porters. So thank you to everybody who contributed to all of this work and to the work which is continuous and ongoing today. All right, I appreciate being part of the National Speleological Society Convention in 2021 and the invitation to conduct this presentation. So if there are any questions for me, you could probably find me in the NSS members directory, and I'd be happy to talk to you further. Great, thanks, and enjoy the rest of your convention presentations.